Okay. I think yes, in the last lecture, we have started our discussion on the last transformation that I want to tell you, which is, we call this diffusionless transformation, okay? Or in particular, we're focusing on the so-called Martensite transformation, okay? So I think we already talked about this, but I still want to point out the differences. So yeah, what is diffusionless transformation? Just to recap what we discussed very quickly at the end of the last lecture. So if you so we know what is diffusion based transformation, right? So all of the nucleation growth processes we have spent most of the course to talk about are diffusion based in the sense that, for the beta phase wants to grow in size, additional solutes like B atoms has to diffuse through the bulk or through the grain boundary, to the growth site in order for the beta phase, which are shown in dark or black here, to grow, right? So it's diffusion driven precipitation, and we work out some very beautiful mathematics for this. But there's another pathway. But in order for this to occur, diffusion usually in solid state occur very slowly, right? So this is a very, very nice processes, and it's controllable in most of the cases. So if you want to have a reasonable size of the grains, you want to control how much of these beta phase you produce, you can use the TTT diagram, which we derived in the last lecture or a couple of lectures before. So you have very nice control of all these processes. But the problem is that you have to be patient, right? You have to wait for the diffusion to occur slowly and control the temperature, etc. But this is one useful pathway. Another pathway is to do the other extreme, right? I don't care about diffusion. I just want to, you have a high temperature solid. I quench it. I quickly lower the temperature by immersing the whole thing, into a very cool liquid like ice water, and I can produce some microstructure. This is called quenching. Okay. Now, typically in these processes, you have, very fast cooling, and all the kinetic energy are taken away. So most of the cases, atoms are just kind of frozen where they are in the solid solution. You won't see any phase growth. But interestingly, as we'll show later in this lecture, that there's another pathway for the system to try to minimize its free energy as much as possible, right? Probably not to the best that they can do, but to the best that to the best they can ever have, but to the best that they can do given the fast cooling, given the corresponding thermodynamic conditions. Okay, so this is what we call diffusionless transformation. So the system, find another way around diffusion, but still to have a transformation to try to lower the free energy in the case of very fast cooling or quenching. Okay, this is basically the Martensite transformation. We've seen this before. So in order to introduce Martensite, you have to induce a very fast cooling rate. This is typically, now it's very, easy to achieve these very fast cooling rate by making very thin film of metallic glasses or things like that. Okay, so we can make very strong materials. Okay, so now what is the thermodynamic driven or driving force for the Martensite? Okay, so in this case, we look at the, let me see. Yes, I got a question. So basically the precipitation and nucleation and diffusion control, the transfer yeah, precipitation and nucleation and growth are both diffusion controlled, right? So you have to, or more precisely, the growth of precipitation is diffusion controlled. The nucleation is also related to diffusion, but more like fluctuations. If you want to see nucleate form, you still have to give the system, enough thermal energy for the fluctuations to occur, right? But the subsequent growth will mainly be diffusion controlled. For quenching, because everything occurs very quickly. So there's so it's okay that you're not turning your mic, but so basically for the quenching, everything just temperature reduced very, very quickly, right? So basically you're taking away all the thermal energy from the system, so the atoms has basically virtually no time to diffuse around. So no diffusion really occur in the quenched system. So that's why it has to find another way to lower the free energy. Yeah. Anyway, so yeah, so now we all know that what is the driving force for the nucleation growth for the precipitates, right? But can we also find a rationale for the other transformation pathway, which is the Martensite? Can we find a reason why it wants to occur by looking at the free energies? The answer is yes. Okay, so this is the free energy that curves that we are fairly familiar with, right? So the horizontal axis is your composition, right? We have focused on the composition of the solutes, which is B atom, and then we have two candidate solid phases we can choose from. One is the alpha phase, the other one is the beta phase, right? And this is a temperature where we know that for a given composition, which is a low composition, so just dissolve a small amount of small amount of B atom in a large amount of A solution. Okay, so this is a very low concentration limit. Okay, at a low temperature, we know this should be what the free energy looks like. Okay, so the alpha free energy is higher for this particular composition than the beta free energy, which is the lower curve, right? But in the case of equilibrium, okay, what you should really have is that in this particular case, right, you have coexistence, so you construct a double tangent, okay, which are tangent to both of these free energy curve. Okay, if I choose this to be my, let me do the notation. If this is my starting composition, right? So initially I'm right here, I'm in the single alpha phase, but because I know that when I separate through diffusion, right, into two different phases, beta phase and alpha phase, right, I can lower my free energy by this amount, right? So now if I separate it into two different phases, I will just do a linear combination of the free energy for two pure phase, right? Based on the, what is the current composition, I can easily pin down what is the actual free energy for the phase separate system. And this free energy, we see that is a huge, compared to the original alpha phase free energy, is a huge reduction. So this will be my driving force for the equilibrium transformation. Okay, now we see that for this transformation to occur, okay, a key thing is that there has to be diffusion, right? Because initially we start with alpha phase, okay, which has this homogeneous uniform distribution of solutes with concentration X naught. But now you have to redistribute all of the solutes into alpha and beta phases with distinctly different composition. Okay, in order for this to occur, we know that we have to use diffusion. Okay, and this is what is, what really happens in the equilibrium transformation case. We have discussed this a lot. Okay, so now let's see, okay, if we take away diffusion, if we quickly lower the temperature, so there's no way for the atoms to really move around. Okay, so in this case, the system going to stuck in the alpha phase forever, or the system can still have a way to reduce the free energy without doing any diffusion. Okay, so what is the meaning that the system cannot do any diffusion? Well, this means that if you start with a homogeneous solid solution of alpha phase, with uniform solutes or uniform concentration everywhere, like X naught, well, if there's no diffusion, this means that you have to end up with another solid phase with identical uniform distribution of solutes. Okay, so this is a consequence of no diffusion. Is that possible for us to have a second solid phase that have exactly the same concentration? Well, and a lower free energy? Well, based on this free energy curve, well, there is a possibility, right? So because for this particular composition, alpha phase, okay, has a much higher, with the same composition, has a much higher free energy compared to the pure beta phase even, right? Now, of course, if compared to the actual equilibrium free energy, both of them have a higher free energy. But if you just compare alpha to beta, they're both single phases with the same composition. Okay, we see that even the pure beta phase with this composition can have a much lower free energy compared to the original alpha phase, right? Well, this is a good indication in the sense that I don't have to change my composition. I just need to, if possible, switch all the alpha phase into the beta phase, and I can keep the composition. I do not have to use diffusion. And this allow me to, by this transformation alone, without changing the composition, I can immediately reduce my free energy by this amount, which is not quite small, right? So where M denote the Martensite transformation, and this delta G is the equilibrium. So without any diffusion, but just changing the crystal structure, keeping the concentration the same, it seems that by switching from the alpha phase field to the beta phase, I can immediately reduce my free energy based on this particular analysis. Okay, so this means that at least I have some driving force to do this, right? Because I can reduce my free energy. It's not the best, but it's a pretty good deal. So the next, I think this is a good indication that is a strong driving force for that possible transformation to occur. But the key we need to answer is that is there a pathway for this to occur, right? This is not going to be a kinetic pathway, but is there a pathway for me to suddenly switch, this alpha microstructure to the beta microstructure, right? So that is the key for this to actually occur. If there's no pathway or along the pathway there's a huge energy barrier, well, then probably you're never going to see this. Does this make sense to everyone? So at least from the free energy analysis, we know, the second best solution is that I keep my concentration the same, which is, required by the system because I lost all the thermal energy. There's no way for me to diffuse around, but I can still quickly switch from alpha phase to the beta phase without changing the composition. Now, if I can do that, I can still lower my free energy. So that's the rationale. Okay. Now, how we should do this, right? Is there a pathway for me to, quickly switch from the alpha phase to the beta phase without changing the composition? That's the key question we need to address. Well, the answer is yes, okay? Because in nature, this already occurred, right? So now how this is gonna be possible, okay? So now in order to answer that question, we need to take a very closer look at the crystal structures, okay? Now, hopefully you've already seen some of this analysis in the other core courses that you have to take. I think the structure and properties of materials. But anyway, so but assuming that we have some knowledge of the FCC BCC crystal structure, not only about their unit cell, but also when I have multiple unit cell put together, we should be able to perceive that what information we can get from looking at a collection of different unit cells. But anyway, I'll try my best to go through this together with you. Anyway, so now basically what I'm showing here, okay, so this is my alpha phase, this is my beta phase, right? Now we just make up the two system. Okay, suppose my alpha phase have a FCC structure or my beta phase has a BCC structure, right? Now you may have the question, which I think one of you already raised this question, what if the alpha and beta phases are not connected by the cubic symmetry? Well, then this will be a different story, but we're gonna use cubic system to illustrate the idea, okay? So you start with an FCC, right? And the beta phase is going to be a BCC. So now in order for the transformation to occur, we have to find a pathway which can allow us to easily kind of transform FCC to BCC. But if we just look at the two cubic unit, okay, you may consider it's not quite possible because the arrangement of atoms are quite different, right? How can possibly these two structure, transform from one to the other without a rearrangement of atoms, without diffusion? Well, so the trick here is that this unit cell, which you typically see for FCC as a cube, right, and with atoms decorated on the center of the faces and on the vertices, it's just one way. Okay, it's just one of many possible ways to represent the unit cell or the fundamental repeating structure for you to construct the whole crystal. Okay, it's not the unique choice. It's just the one conventional, convenient choice for you to represent the structure using a repeating unit. Okay, that makes sense. So there are definitely other ways for you to decompose the large periodic structure into different repeating units. Okay, which will have a more direct connection to the BCC unit. Now, how we can do that? Well, the construction is very straightforward. Okay, so you take these two cubic unit you're very familiar with, right? And in this case, you just consider you arrange them side by side. And this one is 1 cubic. I'm sorry, it's hard for me to show. So this side is 1 cubic. Just follow the pen, and this one is the other. Okay. Now, instead of looking at this cubic, what we do is that now we're focusing on this plane, right? This particular plane. Okay, and this is one of the cubic surface, right? And we know that there's an atom right on the center of this plane. And then what we do is that, okay, we look at then this plane, okay? So which is defined by the two vertices, okay? And this square, okay, defined by the two vertices of the original cube and the particles at the center of one cube and the particle of the center of the other cube. Okay, so this is the square, okay, the edge length, if we consider the edge length of the cube originally is A, I think this diagonal is A, right? For this square, this one going to be the diagonal, and the edge length of this going to be square root 2, I think, over 2 times A. Okay, so this is going to be a square. And then you can define the same square on the bottom face as well, just a identical copy of the one on the top. Okay, so now this 2 square, okay, together with these edges, that connecting them on the vertical direction, define a cuboid, right? So now if we take out the cuboid and also keeping all of the atoms on the vertices, etc., this is the cuboid that we have. Okay, so this cuboid have a squared basal plane and top plane with edge length of square root of 2 divided by 2 times A. Okay, this is going to be the edge length of this. Okay, and then what is the edge length for this height? This is simply going to be A, right? Because we take this from the cube. Okay, so that's defined the cuboid. But if you look at, this is the cuboid. Okay, so it's not a cube anymore. It's a kind of a stretched cube. But anyway, but if we look at what happens to the atoms, this is going to be quite interesting, right? So if you look at arrangement of atoms, you have 4 atoms sitting on the vertices. 1, 2, 3, 4. Okay, right there, and the bottom as well. But now you see that you have a particle that's sitting right in the middle of the whole box, right? It's not on the face anymore, but on the box. Okay, so now this is interesting. Basically, now you see that at least I don't have a cube at this stage, but I have a similar arrangement of BCC. Okay, and this is actually taken out from the FCC. So which means that this is an equivalent way of tessellating the whole FCC structure. You can do this for the entire structure to construct many of these cuboid. I wouldn't be able to show that in here, but I can just outline what you see. So you're not using the original cubic system to look at the periodicity of the FCC structure, but you can perfectly fine using this cuboid, okay, to look at FCC. And then this particular cuboid I'm showing here is a fundamental repeating unit, okay, for that structure. So basically, you can consider the whole FCC is repeating, can be constructed by repeating this cuboid many, many times along the 2 orthogonal directions. Okay, so that is the first step. We see that, okay, now is make more sense, right? Apparently, FCC and BCC do not have any connection if I look at the cubic system, but now if you look at the cuboids, okay, of FCC, you see that, at least I have the correct arrangement of atoms as in BCC. Now, the only thing I have to fix is the edge length, right? Because now it's not a cube. And if I want to transform the structure from FCC to BCC, I have to, deform this whole cuboid so that it can actually goes to a cube. Does this make sense, everyone? Is this clear? Let me see, I think I get a message. Yeah, thank you, yeah. So the edge length is A, yeah. So this is basically our rationale. So before I reach to this slide, the question is that we need to find out a possible pathway, right, for the transformation from FCC structure to BCC structure to occur. And after discussing this slide, I think we now can clearly see a pathway for that to occur, right? Because we already can see there's a BCC-like box in the FCC structure. Now what we need to do is simply to deform this box, to make it more cubic and convert this from the cuboid to a cubic, and then we can actually have the BCC structure. So this is the pathway we're looking for. Is this clear to everyone? Okay, we're looking for a deformation of a FCC structure such that this cuboid, box can be deformed into a perfect cubic box. And this is the pathway we're looking for. Okay, is that clear? Okay, so let me move on. So this is that. Okay, if I don't have any question, assume this is clear. Okay, so now we're one step forward now. So we know there's a pathway, and this pathway involves the deformation of the FCC structure so that I can construct a perfect cubic BCC. Okay, now what is mathematically how we define this deformation? We know that we need a deformation as our pathway to achieve this, right? But what exactly, how we define that deformation, that is something we need to work out in the next step. Okay, so yeah, here's some calculations, and apologize that I use my old notes for the sketch, but I think it's quite clear. So now this is, what we need to work out, right? So basically we know that, okay, without looking at any mathematics, just using our intuition. Now, if I give you a cubic, I'm sorry, I give you a cuboid, right? With the, this edge length is A, where the, sorry, this is hiding the, and then this height is A, and the edge length is square root of A, right? I'm writing down this. So now, in order to make it to be a cube, right? Now, so first we need to find out what is the edge length of the cube in this case. Okay, that's number one thing. But nonetheless, you basically see the height is larger than the edge length of the basal square, right? So this means that if you want to convert this thing to a cube, it doesn't really matter how much you have to do. You need to basically compress in this direction, right? To make this a little bit shorter. And in general, you need to stretch in both those two directions for the, to increase the size of the basal square plane and to compress on the height, right? So this is generally what we need to do. But now we need to figure out what is exactly the amount we need to compress, or what is the exact amount we need to stretch, right? This is, and to achieve a cubic structure. Okay, so this is what we need to work out. Okay, so now the interesting question is that, can we just arbitrarily compress or stretch? For example, can we, because we already have a squared basal plane here, right? This is a very nice square plane. Can we simply keep the size of this plane as square root 2 over 2 times A and compress this edge to the same length, and then we get a cube? Can we do that? The general answer is no, right? Because if we have an empty cube, we can definitely do that very easily. But don't forget, we're looking at the structure, but the structure is not empty. It's not just like a frame that we can do whatever we want, right? There's atoms packing on these structures, and we start from FCC. Okay, what is FCC? FCC is a closed packed structure. So the atoms, they already have their electron shells, touching one another. They do not want any further overlapping, because this is going to cause a huge energy due to the Pauli exclusion effect, right? So we have atoms, which in this particular model, you can consider these atoms as hard spheres in certain, cases. So you cannot cause any overlap between these atoms. Does that make sense to everyone? So this means that you cannot compress the system as, arbitrarily as you want. You have to make sure that the compression or the change of the length of the box does not violate the packing constraints. Okay, so that is, the key that we're going to use to find out what is the magnitude of compression that we are required to impose to the system in order to achieve the transition from FCC to BCC. That makes sense, everyone? Okay. So that's the, step by step. Okay. So now how can we take into account the packings? Okay. So yeah, I don't know why I label this as A and B, but anyway, so because now we have to, go one step backward. So we start from the FCC structure, right? So on this structure, we need to know, okay, how the atoms are packed together. Okay. So now basically we're looking at closed packings, right? So, but we have to identify what are the closed packed planes. Okay. So the thing that we need to look at are, so if now I increase the size of the atom, which I think I do it here. Okay. I label the plane A and B here. So A is the top basal plane. Okay. A is this plane, and B is the diagonal plane that I highlight for you. Okay. So here I showed you what is the packing arrangement of these atoms on B. Okay. So first, B is a square. I'm sorry, I think I have a request. I need to. Okay. So B is a square, right? So this is a square. of the plane. Okay, so what is the square, the length of the square for this plane? The edge length for this is A, right? Because this is the height that we get. Okay, and then this edge is gonna be the face diagonal, which is can also be A that we have. Okay, so this is gonna be a square, okay, of edge length A. Now, what is the plane defined by this top surface A? How the atom is going to look like on that packing. So we know that this A can also be a square, right? But that square going to be smaller than this one. Okay, the square going to be a little bit smaller, like this. And on the square, the atoms are packing this way. I'm sorry, this is a very bad drawing of atom, but you get the idea. Okay, so they're going to touch one another at the center of the edge. Okay, that this makes sense to everyone? This is, we're not doing anything new. This is just from the, the typical understanding of close packing from the FCC structures. Okay, so now with that, we can, and then, try to make connections. Okay, so this is for the FCC, right? So we from the cuboid, right? But how can we connect this cuboid consideration to the BCC? Okay, now for the BCC, we see that, this is a BCC structure, right? So, you deform, you stretch this two edges, you compress this edges. But what is not changing is that, okay, if you look at the basal plane, I'm sorry, if you look at the diagonal, right, this guy, right, the diagonal plane on the BCC, okay, now in the FCC, things are touching, like this. In the BCC, we know that things also touches one another, right? There's one thing that's not changed, from this transformation in FCC and BCC. One thing is not changing, okay, which is that this length, okay, and this length does not change, right? Because in BCC, we know that all the atoms can touch also through the body diagonal, right? And in this case, they also touches through this diagonal, okay, which is right here. Okay, so this means that this length does not change, which equals to 4 times the radius of the particle. Because, in this case, you have 1 radius, 2 radius, another 1 radius, 1 radius, 2 radius, another 1 radius, right? So this line, it doesn't really matter how you stretch and move these two atoms around, but this line does not change. Okay. Now knowing this, and then we can actually, so this is a key that allows us to connect the edge length, okay, of this guy. So I call this, now I change notion, I think, because here I use L. So now basically I'm calling the height here, this one as L, okay. And then I call because now this is a cube, so I call the edge length of this cube in the BCC case as L prime, okay? And I call this height here to be my L. And this L is also the edge length of the square that I just have right here, okay? So now the condition we have is that because this diagonal equals to this diagonal, okay? Now, if I write down this diagonal, which is diagonal of a square, which at edge length L, okay, this diagonal simply equals to square root of 2 times L, right? Now, this diagonal is the body diagonal for that cube. Now, if the edge length of the cube is L prime, this body diagonal, the length of this body diagonal is simply equals to square root of 3 times L prime, where L prime is the edge length of the original cube for the BCC, right? And from this analysis and from the packing constraint, we know that this two equals one another, okay? So because they have, this is the same body, the diagonal, along which 3 particles touches one another, okay? And based on this equation, we can easily solve what is, L prime in form of L, right? So basically we can solve L prime simply equals to what? Square root. And inside of this, we have 2/3 times L. Okay, so this is what we're looking for. Okay. So does this make sense to everyone? So we know that we need a deformation of the original cuboid to induce this transformation. Okay, and but we don't know exactly how much we need to shrink on one side or stretch on the others. So the way we do is that we use a packing constraint to find out exactly, or before and after transformation, what has changed, what has not changed, and this allows us to find the relation between the edge length of the BCC cube after transformation, which is L prime, to the original height of the cuboid before the transformation. Okay, and we have this relation. The edge length of this of the BCC cube is simply equals to square root. Inside of this, we have 2/3 times L. Does this make sense to everyone? Okay, so this is what we have. Now, once we have that, I think the next step is very straightforward, because now we know, okay, what is the edge for this cube after transformation? We know all of the edge lengths for this cube before the transformation, right? So it's very easy for us to now find out, how I should quantitatively deform this cuboid to achieve this cube, right? So that is quite clear. Okay, so now I'm going to do that. Okay, so let me clear this. Is this analysis clear? I didn't get any feedback today, but I hope this is an indication of everything is clear. Okay, so now if this is clear, the thing we want to do is that we need to find out exactly how we stretch each edge or compress each edge in order to achieve that particular deformation, right? So now I'm writing down the numbers for you again. So for this one, I have L prime, right? This is the length of all the edges and heights for the box, which is square root of 2/3 times L. Okay, and for this big guy, for this original FCC box, I have this height equals to L. And what is this edge? This is square root of 2/2, or square root, and then you have 1/2 times L. Okay, so this is the edge. So now if we compare, for example, because basically we know that we're going to compress this box in the Z direction and stretch this plane in the X and Y direction, right? This is roughly, we analyze from our intuition. Now we're going to find out quantitatively how much I have to do this deformation. Okay, so how much we need to compress? Okay, what is the original length before the compression? L, right? Because this is a height direction. Now I'm talking about compression along this vertical direction. What is the height after the compression? This guy, right? Now, how much I have to compress in the Z direction, in the vertical direction, in terms of a strain? How do we find out that? Well, what is the definition of strain? Well, you take the new length, which is L prime, you minus the original length, which is L, you divide this by the original length, right? You get a relative magnitude of deformation with respect to the original length of the system. Does that make sense to everyone? Okay, so yeah, so basically that is the definition of the strain in the Z direction. You plug in the number, okay, and we can cancel all the L, right, as a unit. And then the number you have is square root of 3, 2/3 minus 1. And clearly you see that this thing is going to be a number smaller than 1. Okay, so you're going to get a negative strain in the Z direction. But what is the meaning of negative strain? Where you get compression instead of elongation. Does this make sense to everyone? Okay, so now for the X and Y direction, what you need to do? Well, very similar. What is the length after the deformation? This one, right? L prime. What is the length before the deformation? Square root of 1/2 times L. And then you basically get the difference. This is my delta X per se over original length, which is the length of the this basal plane edge, okay, which is square root of 1/2 times L. Again, you can plug in the numbers, and this is what we get. Okay, so now you have a positive number. What does this mean? Well, you have to stretch along the X direction. Okay, now for the same analysis, you can do the Y direction because X and Y are symmetric, so you get exactly the same results. So now these analysis, quantitative analysis clearly confirm our intuition, right? Because this is a cuboid, so you have to compress in the z direction and probably stretch along the x and y direction to increase the size of the basal plane and decrease the height, so we can have this BCC cube, right? And this is exactly what we have. And more importantly, not only we find out, you have to do this stretching compression kind of deformation, you know exactly what you have to compress and what have to stretch in terms of strain. Okay, so this is basically what we find out. Okay, so this is the transformation pathway. Okay, so now you see we're in a very good position, right? So we start from the free energy analysis. We show that there is a clear driving force for you to do the transformation without changing any composition. You can directly induce the transformation from alpha to beta without diffusion, but this allows us to lower the free energy. And this we see this is a driving force. And now we also see there's a pathway to do this. It's not a kinetic pathway, but it's a deformation pathway, right? So we can achieve the transformation from alpha to beta, from FCC to BCC through this very interesting combination of deformations, by compressing in the z direction and stretching along the x and y directions by this particular amount, right? And you can have that, okay? So this seems very reasonable. Okay, we have a driving force, we have a pathway. Now the question is that, okay, is there any barrier that I'm going to deal with? Okay, so I think for the barrier, I think I need to clarify a few things. So we know that by doing the transformation, you can actually reduce the thermodynamic free energy, right? As we showed from the free energy plot. But during the processes, does this processes, cost any work, cost any energy to achieve?
For volume change.
From volume change, exactly, right? Because we say you have to deform the box, and deform meaning that you have to, involve some mechanical energy in the system, right? Either, you can apply energy to the system so it have this deformation, or this occurs spontaneously due to the thermal driving force. But this is going to give you a change of volume, right? Which can or cannot be compatible with your original structure, and this possibly going to contribute to an increase of energy that's going to serve as your barrier. Okay, exactly.
But Professor, the volume is same, right?
No, the volume is not. The volume changed because all the edge lengths change. If you compute the volume change, which I will show you later. Let me clear this. But this is the possible, right? At least we cannot guarantee the volume is the same. So there could be a mechanical energy involved in this, right? So now we're going to show that. Yes, this is basically another way of looking at this whole thing, right? So in here, I'm actually looking at the very single unit cell, but if you want to go back to the full structure, okay, so the stretching is not on the original X and Y. If you look at FCC, the original X and Y will be along this orthogonal direction, but now the actual stretching direction will be, or the expansion direction will be along this diagonal, right? But z direction is the same. So we're gonna need, roughly speaking, 80% of compression along the z direction, and you will need 15%, 15.5% of expansion along the two diagonal. But this is how you apply, what we obtained from the previous analysis to the actual structure. Okay, this is one thing that I think I want to point out. I get some message on the chat come from the original side. Yeah, the square root of 1/2 is the same as square root 2/2. Yes. Okay. Anyway, so this is how you apply the local analysis to the global FCC structure. Now for the volume. So does this change the volume? Well, the answer is yes. Let me see. Do I have a calculation? Yes, this is a volume. Yeah. So anyway, so let me see. What do I have for this? Yeah. So this is a typical consideration that how you would do that. Okay. So this part, I think you have a homework, I guess, for this. So Martensite transformation. Yes, this is about that homework. And then the first question asked for you. So this is just a little bit fancier way of showing the different type of atoms, but you get the idea. It's basically the same as what we did before. It asks you to compute the normal strain component, achieve the transformation, right? So we all compute this all together. I think I go through this in detail, we should have no problem about that. Now, here's the volume. Okay, so is there going to be a volume change? We don't know, but let's compute, right? It's very straightforward because you have a cuboid before and you have a cube after. So the calculation will be very straightforward. Let's first do the volume after. Let me see, I get the chat message. Okay, it's fine. So let me yeah. So let's do the volume after because it's easier. After this, what we have is just a cube, right? And this cube have edge length of L prime, which is square root 2/3 times L. We simply take the cube of that whole thing, and that's gonna give us the volume after, right? This is quite clear. Now, what is the volume before? Well, the volume before is this guy, right? This is the cuboid, and we know that the basal plane is a square, so we have this edge length of the square. You multiply those two together, you're gonna get the edge length. I'm sorry, the area for the basal plane, and then you time the height, which is L, right? So basically, what we have here is 1/2 times L, I believe. And in here, you have a very funny number of, this whole thing, a cube, I think. 1/2 L cube. And this one going to have the square root of 2/3, okay, and times 2/3, okay, times L cube. Okay, so clearly these two numbers are quite different. Okay, so you have a change of volume. Does that make sense? Okay, so and then you can define this question, I think, guide you through to define the change of the volume, which is V after minus V before. So you take this V after minus V before and divide it V before, and this actually allows you to compute a overall change of the volume. Okay, so and basically there is a change of the volume. Okay, and this as we can see, if we have a change of the volume, this means that if some region of the system have or undergoes a Martensite transformation by switching from the FCC to the BCC, well, this means that you're accumulating a possible string energy, right? Because you have a volume change, which is not small. This is fairly large volume change, like a 10% at least on that level, right? So let me clear this and forward. Okay, so and if we do that, I think I don't have a calculation for you, but you can get a rough estimates because along each direction you have like 10% change, and then the volume at least will be on this level, right? It won't be smaller than this. So and this is going to give you a volume energy, right? And how can you compute the strain energy? Well, you get the volume strain, and then if you follow this, basically I give you the bulk modulus of the material, and the roughly speaking, the strain energy per unit volume is like a spring, right? You stretch the spring or compress the spring, and the spring constant, and then you can basically get energy stored in the spring. That's the same idea, but now you convert this to the strain energy. You look at the volume strain and bulk modulus for this, so you get a number and compute, and this is going to be your barrier, right? So basically this means that, okay, thermodynamic wise, I do want to do the transformation because it's going to reduce my free energy, thermal free energy. But on the other hand, there's no guarantee, and usually not quite possible, that the entire system going to all undergo the same transformation simultaneously. So I want to be able to convert the bulk of alpha to the bulk of beta. Usually this can happen within a narrow, in a certain region, right? So in order to accommodate, these strain energies, so typically what happens in the system, which I don't have time to really go through in detail, but I just want to point out, is that there is a driving force for you to do the transformation, but also is going to accompany it with a very high energy cost due to this mismatch of the volume. So the nature has a very smart way of solving this. So the basic idea is that you arrange these transform the regions side by side. Okay, you create a kind of a mirror image of the transformation. So we call this a twin boundary. So it's like you share the system. Okay, when you do the transformation, you don't just insert one solid into the other, but you share the system to create a kind of shared band of structure, and this will actually, allow you to accommodate the actual change of volume, but not increase too much of the strain energy. Okay, I'll stop at this level because I think you're probably going to see this in more detail in the physical metallurgy class. But for now, I'm just so this is the highest level I'm going to mention. So, thermodynamics wants a transformation, but the transformation going to have a higher strain energy associated, and the material find a way to release that strain energy to create these shear bands and twinning structures. That's the whole story. Okay, so and this is a mechanism. I do think I have some images to show this. So basically, all of these structures you see, all right in the middle of the grain, these are not by any nucleation and growth processes. These are the trace of Martensite transformations, and in particular these twinning, structures where that you have kind of a release of the very high strain energy built into the system due to the transformation. Okay, so that's basically the Martensite. Okay, I think pretty much, yeah, this is all I want to tell you about this. Okay, so again, we're not going to discuss this in any detail for this class, but we just want to bring up this as an example for the diffusionless transformation, in contrast to all of the diffusion-based transformation that we discussed, right? So this is due to faster cooling, so there will be no diffusion around. And so the system has to find another way to reduce the free energy. Okay, and we see that you can keep the concentration the same, but simultaneously change the structure from alpha to beta. Thermodynamically, there is a driving force for that, and we see a realization of pathway. It's more like a geometrical, pathway that we deform the box, right, from the cuboid to the cubic, by also considering the constraint of packing, and then we show that this is a doable but necessary to introduce a huge elastic energy and as possibly a barrier, and the material have a very smart way to compensate these free energies by developing this twinning and structures and boundaries. Okay, so that's basically complete what I want to tell you about this transformation. And again, as I said, this is the last transformation that we discuss in this class. So this basically concludes all we want to discuss about the new topics. Okay, since we still have some time, which I reserve, I can quickly go through the homework with you. Okay, so but before I go through the homework, any questions for the Martensite transformation? Okay, so basically we're already done with this one, right? So I'm sharing my screen of the homework. So it has 3 questions. I think we just finished this one, the Martensite transformation, right? Let me see if there are any new things. So this is the setup we just described before. You have side-by-side 2 FCC in the cell, and it's a Martensite transformation. Asks you to compute the strain to deform the box. We compute all together. I showed you the results. Compute the volume strain. I also went through all this together, and finally compute the elastic energy due to the change of volume. So it's very straightforward, and I think you should get a number. Okay, so this part should be clear. Okay, so the first 2. Yes, this first one is the JMAK equation. This is for the TDT diagram. So in class, we derived the equation describing the overgrowth dynamics in early stages of the precipitation. During which the overlapping of the precipitate excuse me, particles can be ignored. So now assume the overlapping between the precipitate phase particles cannot be ignored. For the side saturation case, make a guess of the associated JMAK equation. I think we already showed what this looks like, right? Prior to reasoning or justification for the guessing A. Okay, I think in one early version of this class, I actually asked the class to derive this equation, but I think it's probably too much for you to do this independently. So then I reduced the difficulty level. So the idea is very straightforward, right? What is the JMAK equation? JMAK equation tells you, the fraction of the phase that has transformed as a function of time, right? This is what we need to do. And we know in the early stage, what this looks like is that you just have, the number of particles divided by the volume, and then you times the volume of each particle as a function of t, right? So this is very straightforward. This is the volume of the system. I could call this the VT. But if you group these two together, n over VT, this is what we call the number density, right? The number of particles in the system per unit volume. This is simply that. Okay, so this is in the early stage of your system, right? And VT, we know it's just grow as a function of time, so this is easy to do the integration and find out that. Okay, so this is what we show in the class, right? But now let's think about this. Instead of looking at it, because we already write down this as a solution of an equation, but how about we write down this in a differential form, right? Instead of writing down f as a function of t as a rho times the volume of particle as a function of t, let me write down the differential form. I consider the change of f, right? And how the change of f is related to the change of volume for a very particular, during a very small time period dt. I consider that. Okay, so basically we're constructing a differential equation based on the very intuitive understanding of the system. Now in the initial stage, this is very straightforward, right? Because we know differential operator is a linear operator. So this is the equation you have. You just apply the differential operator. This is what you're going to have. df, the change of that, fraction of that transformed phase equals to rho, has nothing to do with time, times dv. Does this make sense to everyone? Okay, so it's very straightforward, right? In class, we discussed this. Now we want to move one step forward. We find a differential form of this equation. Okay, so now what is dv? Well, v is what? If we have, spheres, this is 4 over 3. I'm sorry for writing of 3. This is r cubed, right? But what is r? R is v gross velocity times t, right? So it's very straightforward to write down. If you want, you do not like dv, you can easily plug in dv in terms of time. So you have df as a function of time. Yeah, this is very straightforward to do. But let me write down this. I think it's probably more straightforward of the meaning. So this is in the very beginning stage of the growth, right? For which we consider the particles are independent of one another. So, every single increase of the volume of the particle will contribute to the increase of the overall fraction of the transformed phase, right? That this is in the early stage where the particles are not, overlapping one another. But what happens, and what do you think that how, in the later stage, or not in the too early stage, when the two particles grow like that, each of them going to have an independent increase in volume, but because they have this, overlapping regions, not all the increase of volume, this dv, gonna all contribute to the increase of df, right? Only a portion of increase of the particle volume gonna contribute to the increase of the fraction. Does this make sense to everyone? Okay, so in the later stage, only a portion of the increase of the volume for the individual particle going to contribute to the growth of the fraction, right? In the early stage, all of the increase of volume going to contribute to the increase of the fraction. But in the later stage, only a portion going to contribute. Okay, so what is that portion? Well, so for that one, I will not ask you to derive, but is in the first order approximation, that portion we can simply consider is proportional to the available free space in the system. Okay, so this is the correction to that equation. This is okay in the very early stage, but towards, as f increases, okay, the growth of the volume for the individual particle only going to contribute a portion to df, and that portion we consider is proportional to the free space in the system. Okay, what is the free space, or the fraction of free space? Is 1 minus f. So this is the full equation. Okay. So, and clearly you can see what happens, for different values. For F is very small, like very close to zero, you simply recover this one, right? For the early stage, all the volume going to contribute to the change of F. And when F is very close to one, you see that the F is almost a constant. It's not going to change no matter how you grow the volume because they're all saturated, right? So if you solve this equation, it's very straightforward to solve, which I want to do that for you. So you just move this here, and then on this side you have dv. I think if you solve this equation, you can easily get this f, okay, equals 1 minus exponential, okay, and I think probably minus v or something like that. I can't remember exactly, but v is simply this thing, right? So you plug this back in here, and you can recover the JMAK equation we derived for the site saturation case. Now, if you do not want to work with v, you can plug in t here, but you can do the same calculation and you get the same results. Okay, so that for part one of this problem. Okay, so I think the cutest thing is to realize this part. I think this is one of the interesting observation. Any questions?
I had a question about part one. So basically, when you substitute dv with time, so does that mean I have to differentiate 4 by 3 pi v cube t cube as well?
Yeah. So so this is v, right? So you have to differentiate this. So I think that if you plug this by time, let me write down that for you. You don't have to work with time, but if you want, you can do that. So I'm just working on this. So if you plug in here, dv simply equals to d. This is a differential operator, and then you have this 4 over 3 times pi, right? And then you have v to the cube, and then t to the cube, right? But all of these are constant, so just to take them out. And then when you take it out, you get this. And you have dt cube. Okay, if you want, you can take this out as well, but I don't think you need to because you're eventually going to integrate on both sides of the equation. So that answer your question?
Okay, so it will be 4 by 3 pi v cube dt cube.
Yes, because when you do the integration, it's very straightforward. You take this differential sign out, and you have everything you want, right? You can take it out. You can say this is a 3 and t squared and dt, but when you do the integration, you have to go back to the d cube, right? You know what I mean? Because you have to integrate the equation to solve for f as a function of t. So you don't have to really do anything like that because eventually you want this.
Okay, thank you.
No problem. Okay, so that's for this one. I think is quite clear. Okay, so now let's go to the next one. The Spinolo decomposition. This one is very similar to homework one. Okay, so in homework one, we have a problem which is not about Spinolo decomposition, but about the construction of the phase diagram, right? Using MATLAB or other mathematical numerical tools you're familiar with. For that one, I give you a much complex free energy, but the idea is very similar. In those cases, in that problem, the free energy is not symmetric, right? So it's not quite too possible or realistic to solve this problem analytically. But here I reduce the complexity and make the problem very easily solvable analytically. So this is a very simple symmetric regular solution model, right? So this part is entropy, this part is enthalpy, and this is the original free energy of the two, the mixing case. And here we consider half-half mixing. Not necessary, but everything is symmetric. So this is quite simple to do. So yeah, let me see. So this is the setup, right? And I give you omega is greater than 0, which is 0.5, which means that the system from the enthalpy point well does not want to be mixed together, right? Entropy wants mixing, enthalpy does not want mixing. So in principle, there will be a phase transformation at some temperature. First one, determine the critical temperature T star as a function of B atom composition, below which the two-phase coexistence is thermally stable. So what does this mean? Okay, so Um, we're not quite familiar with the statement, right? But if you suppose that, let me show you the phase diagram. Okay, so now if we were looking at this temperature T, right, and we're basically looking at a very symmetric phase diagram like this. This is going to be my X, right? So this will be the miscibility gap we have, right? So what we typically familiar with is that, okay, I give you a temperature, right? For example, T, and you tell me that, okay, at this temperature, what are the two equilibrium, composition? In here, these two are symmetric. So if you know one, it's very easy to map to the other one. Okay, so this is something we know how to do, right? So how we get these two composition? Well, we can do the double tangent construction. Now in this case, because the free energy curve is perfectly symmetric, so we know the double tangent construction can always give us the two local minimum, right? So using all these analysis, there are many, many different ways you can simplify the problem. Okay, but the idea is still you do the double tangent construction, and then you can easily find out what is the composition for a given temperature, what are the corresponding composition that make the system to be, within the composition that the system are stable as two-phase coexistence. I get a question. Yes, the critical temperature will be in terms of T, because X is also going to be a function of X, but X is dimensionless. So basically this is what we know, right? But if you look at the question, what is asking? Well, what is asking is that if for a given composition B, let me show that. So instead of giving you a temperature, but I give you a composition, right? So this is my X. I ask for this given composition, what is the critical temperature T star, okay, for given composition that below which the two-phase coexistence is stable. Now, for a given composition, how should I find that T star? What do I need to do? Well, I just need to do a composition axis, right? Okay, I start from high temperature and I start to lower the temperature, and that's going to be my T star. Does this make sense? Because this is for the given composition, what is the lowest temperature below which, let me see, what is the critical temperature below which, the two-phase coexist is stable. So this is going to be my T star, and this is for one X. Okay, what if I change X here? This is going to be my new T star. If I change X here, this is going to be my new T star. Okay, so this will allow me to actually find out what is T star as a function of X. Does this make sense? Okay. Well, but the thing is that it doesn't really matter whether we write down T star as a function of X or T as a function of, or X as a function of T. What you're looking for is the same curve, right? What you're looking for is the same curve that separate from the solid solution state versus the two-phase coexistence state. You're looking for exactly the same phase boundary here. Okay. So, and you know how to do that, right? Because you can easily find out what is X as a function of T, and you can invert this very easily to find T star as a function of X. Both of these two equations define the same curve, which is right here. Okay, so that's, if you realize that, well, this is very straightforward, nothing really new, but just a different way of looking at this phase boundary. Okay, now for B, determine the composition XB at which the T star is maximized, and determine the corresponding maximum value for T star max. Okay, if we look at now, suppose now we're actually looking at T star as a function of X. I know that, okay, if I increase X, right, from here, okay, I increase T star, right? So how can I find out the maximum? Well, if you have an expression of T star as a function of X, what you can do is just mathematically, you take the derivative of T star as a function of X, and you set that derivative equals to 0, and you can immediately find out this X gonna equals to a half in this case, okay? Now, graphically, this is also the same thing, right? You have a T star as a function of X. Well, clearly, this is when X equals to a half, because of the symmetry of the system, you get the maximum T star, and you can plug in that value and then find T star max. Okay, so this is that. I think determine the equilibrium composition of the two phases at T equals to 0 point T star max, and this will be something here. Again, very straightforward. You plug in the value for that, and you can get, I think, numbers, okay, for these two. Okay, so that's that. Determine the composition that define the chemical spin nodal. Again, it's very straightforward. The chemical spin nodal is you take the second order derivative of the free energy functional as a function of x, right? So you basically you basically have this second order derivative of free energy with respect to x and equals to 0. From that, you can solve for the chemical spin nodal. It's very straightforward and plug in this. Okay, this is the yeah, and this last one is about the energy barrier. Okay, and so this is again we discussed this in the lecture slides if you still remember. Okay, we have a driving force which is proportional to the second order derivative of this guy, right, in the chemical spin nodal, and then you know how these other parameters contribute to the interfacial energy increase and possibly a bulk free energy. I'm sorry, a string energy increase. Okay, we simply use those considerations, and then you can find out what are asking for here. Okay, so I think that's pretty much all I want to say about the homework. Again, I think it's not quite difficult once you realize what I'm asking for. Is basically is on the same object but looking at different perspectives. Okay, so with that I'll stop. Okay, let me stop recording. So I'm basically done for this class. Okay, let me see, stop recording.